This is the solution to question 6 on the complex differentiation tutorial sheets, the second part of the tutorials. The question states that suppose f of z and its complex conjugate f of z star are both analytic. Show that f of z is constant. The only hypothesis we've got to work with is the fact that f of z and its complex conjugate f of z star are both analytic. Now, analytic implies that the Cauchy-Riemann equations are satisfied. So the first point we're going to try and do is we'll split f of z into its real and imaginary parts. Its real bit being u of xy and its imaginary part being v of xy. We therefore get that u and v must satisfy the Cauchy-Riemann equations. This follows since f of z is analytic. This is always a good starting point if the only thing that you're told is that a particular function is analytic. Writing down the Cauchy-Riemann equations will often send you on your way to actually solving the problem. Now, we also know that the complex conjugate of f, which is now going to be u of xy take away, because we've taken the complex conjugate, I of v of xy, is also analytic. So it will satisfy the Cauchy-Riemann equations as well. But the Cauchy-Riemann equations for the u term will be exactly the same, because the real part is unchanged. However, the imaginary part of f of z complex conjugate now has a minus sign in front of the v. This changes the signs in front of the v derivatives. Now, that is all that the question actually tells us at the moment. From here on in, we're making deductions from these two equations. So let's write out those two sets of equations again. So the top equation gives me, or was the conclusion from the Cauchy-Riemann equations from the analyticity of f of z. The bottom set are the conclusion from the analyticity of f star. Now, you should notice that we have similar terms in there, so we can now equate them. So equating those two terms, we get dv by dy is equal to minus dv by dy, and similarly dv by dx is equal to minus dv by dx. Now, the only way that those terms can be equal, a number can be equal to its negative, is if both are equal to 0. So we now know that the derivative of v with respect to y and v with respect to x is 0, and that means that v is constant with respect to x and y, so it's a constant overall. So we've now shown half of the question. We've shown that the imaginary part of f of z is a constant, and we can now use this together with the Cauchy-Riemann equations to deduce that the real part must also be constant. So taking the Cauchy-Riemann equations, we must get du by dx is equal to 0 and du by dy is equal to 0. And that follows looking at the Cauchy-Riemann equations and just substituting in the fact that v is a constant, or equivalently, v's derivatives with respect to x and y are both 0. So again, this implies that u is a constant with respect to x and y. So overall, we now have that f of z, which is u of xy plus I v of xy, must be c plus id, where both c and d are constant real numbers, and that must be equal to k, where k is a constant complex number.